Welcome students to Program Bachelor of Science 3rd year, Subject Botany, Semester 6, Course Code BOC 108, Course Title Cytogenetics and Plant Breeding. The title of Unit 4 is Linkage, Crossing Over and Chromosome Mapping. Module name is Interference and Coincidence. I am Ms. Marina Janice Rodriguez, Assistant Professor from Dempe College of Arts and Science, Miramar, Goa. In this module, we will be learning about interference and coefficient of coincidence. By the end of this module, you will be able to define interference and coefficient of coincidence, compute interference and coefficient of coincidence in a given problem, state the conditions for positive and negative interference. You know that crossing over is caused by the exchange of sections of homologous chromatids at meiosis. There are two types of crossing over. A single crossover is the product of single exchange of sections between chromatids, whereas a double crossover results from chromatids being involved in two exchanges. In higher organism, it has been observed one chiasma formation reduces the probability of another chiasma formation in an immediately adjacent region of the chromosome. It is probably because of physical inability of the chromatids to bend back upon themselves within a certain minimum distance. This tendency of one crossover to interfere with the other crossover is called interference. The strength of interference varies in different segments of the chromosome and is usually expressed in terms of coefficient of coincidence. Coefficient of coincidence can be calculated by this formula, which is the division of observed double crossovers and expected double crossovers. On finding the interference, we can calculate coefficient of coincidence, which is represented with capital C. We use the formula interference, represented as capital I, is equal to 1 minus C. Let us consider a cross of homozygous dominant, capital AA, BB, CC, crossed with small letter AA, BB, CC. F1 generation would give us capital A, small a, capital B, small b, capital C, small c. We carry out a cross of this F1 individual with homozygous recessive. We get the following observations. Let us now denote the parental type, the double crossovers and the single crossovers. Notice the most abundant values, that is 300 and 400. These two are the parental types. Now notice the least values in the observation table, that is 10 and 15. These are the double crossover types. The intermediate ones, that is 90 and 80, and on the other hand, 50 and 65 are single crossover types. The next step is to find the gene order on the chromosomes. To find the gene order on the chromosomes, we compare the parental types and the double crossover. Here, we notice that gene A has switched its place. That is why gene A will be placed in the middlemost position on the chromosome. Thus, we get the gene order BAC. The next step is to determine the distance between the genes B and A. We consider the relevant single crossover here, and we use the formula distance between genes is equal to single crossovers plus double crossovers divided by the total number of progeny multiplied by 100. We get the values as 90 plus 80 from the single crossover, adding to the double crossover, that is 10 plus 5, divided by 1000 multiplied by 100. We get the value 18.5%. Similarly, to find the distance between A and C, we compare the relevant single crossovers. Here we see that C has switched its place, and that is how we come to know which single crossover to consider. Following the same formula, we get distance between gene B and A will be equal to single crossovers plus double crossovers divided by the total number of progeny multiplied by 100. In this case, the single crossovers are 50 plus 65, adding to the double crossover, that is 10 plus 5, divided by 1000, multiplied by 100, giving us 13%. Based on the genetic map, the expected double crossovers are 0.185 multiplied by 0.13 is equal to 0.024. If we have 1000 progenies, we get the expected double crossovers by multiplying the value which we have just calculated, that is 0.024 by 1000, which gives us 24. When we observed in the observation table, we saw that the double crossovers were 10 and 15 respectively. On adding that, we get 15. But the calculated double crossover was 24. The calculated double crossover was the expected double crossover, whereas the observation table was showing the observed double crossover. Clearly, we have seen a reduced value that was obtained in case of double crossovers. This reduction was because of interference. To calculate the coefficient of coincidence, we use the formula coefficient of coincidence is equal to observed double crossovers divided by expected double crossovers. Our observed double crossover was 15 and the expected double crossover was 24. The division gave us a value of 0.625. To find the interference, we use the formula interference is equal to 1 minus coefficient of coincidence. We get 1 minus 0.625, that is equal to 0.375. If interference is complete and there occurs no double crossover, then the value of interference is 1. If fewer double crossovers than expected occur, interference is a positive number and positive interference has occurred. If more double crossovers than expected occur, interference is a negative number and negative interference has occurred. Positive interference is most commonly observed in eukaryotic systems in general. The closer genes are to one another along the chromosome, the more positive interference occurs. These are my references. Thank you.